Hello, this video is introducing working with systems of differential equations. What do I mean by that? Well, a system is more than one differential equation. Here's some differential equations here. And we use them quite a lot in the real world where we've got variables and more than one of them, and they're all connected up. But they're not only connected up simultaneously, but they're through differential relationships. So, for example, foxes and rabbits. Well, if there's more rabbits, there's more for the foxes to eat. If there's less rabbits, there's less for the foxes to eat. So the populations are connected. Chemical factories, the amount of reactant we put in affects the amount of product that comes out over time. Pollution, particularly lead pollution in the body, the amount coming in, the amount going out. And even more interesting at present, sort of pandemics like COVID and how they operate. So what we're going to do in this first video is look at as how we solve these sorts of systems here of differential equations, simple systems. So let's have a look at an example. Foxes and rabbits, then, often called predator and prey. So I've got that F is the number of foxes, R is the number of rabbits, and we know they're connected together over time. So on the left-hand side here, we've got rates of change, the differentials, yeah? And on the right-hand side, to keep in the simplest version, we have linear combinations, yeah, of the number of foxes and rabbits. So here's a linear combination. There's an F, there's an R, and they're just multiples, aren't they? You've just got coefficients out the front. They've got different coefficients for these different equations. And what's this telling us here? So let's just have a look at this first one. The rate of change of foxes over time, it will increase with the number of foxes. Well, if there's more foxes, they're going to breed, we're going to have more foxes. But it's also going to increase with the number of rabbits, because if there's more rabbits, there's more food to eat, isn't there? So that's going to go up. Have a look at the rabbits one. Well, it's negative with foxes. So if there's more foxes, they're going to eat more rabbits. So the rabbits are going to go down in number over time. And if there are rabbits, well, they're going to reproduce over time. So there we have an increase. So that's explaining roughly what these differential equations are doing. And what we're going to do now is look at how we solve them. Yeah, these are two differential equations. And I've got to decide which of our variables I'm going to solve for first. So I'm going to solve for foxes. So if I'm going to solve for foxes, I need to get rid of the differential, the r's from these equations. There's an r there, and there's a dr by dt there. So I'm going to start by eliminating the dr by dt, and then I'm going to go on and eliminate the r's. Yeah. So let's have a look at the eliminating dr by dt. Well, I've only got one equation with dr by dt in. If I want to get rid of it, I need to create a second equation with dr by dt in, and I'm going to do that by playing around with this top equation here. So let's have a look at that, shall we? Here's the first equation. df by dt equals some function of f plus some multiple of r. So if I just differentiate this equation, now I've got a second order in f on the left. I get first order differential in f there, and I've got a first order differential in r here, dr by dt. I want to get rid of dr by dt. Well, I've got an equation from above in terms of what happens to the rate of change of the rabbits. Here it is, the second equation, and it just tells me what dr by dt is in terms of f and r, so I'm just going to sub that in place of the dr by dt. So I've now got this equation here. Well, which I'm trying to solve, I'm trying to get it all into f, aren't I, so I can solve it. So look at the one at the bottom. Well, that's in f, the second differential. I've got first differential in f, and I've got another pattern multiple of f. So I've just got this r to get rid of now. Well, how am I going to get rid of that? Well, I'm going to go back to my first equation. Here it is. df by dt, some multiple of f gives me r. Some multiple of r. Well, I want to make r the subject to this equation, yeah, so if I subtract this one term and I divide by 0.14, so 0.4, there we go. I've now got an equation for r in terms of f. And looking back at my second order differential equation I created on the last page, well, I've got something now I can put in place of the r. So I just substitute that in place. Here it is. There we are. Now I've got an equation entirely in f. I can tidy this up, this equation, because I collect up terms. Those two are both first differentials. These two terms are both just multiples of f. If I do that and group them up, I get this equation here, having collected up the terms, which some of you will notice is a homogeneous equation. If I rearrange it, second order differential equation in f, isn't it? We would always usually set it up like that with a 0 on the end. So I've got a second order, a first order, and the value itself and the differentials. And we know how to solve that, don't we? Here we go. What do? We use our standard sort of exponential solution. Here it is. F is some function of multiple of a e to the zt. I've put z in there because my solution to my auxiliary equation, it could be a complex number. And in this case it is. Z is going to be 0.15 plus or minus this imaginary part. So what's the solution look like? Well, the solution looks like the 0.15 is an increasing exponential, isn't it? That's going to give us our exponential like that. The imaginary part's giving us a combination of cos and sine, which is going to be an oscillation. There we are. So we've got a solution for f, number of foxes. Now we need to get a solution for number of rabbits. So there's the foxes. Here, going back to our equation 4 we created earlier, we found an equation for r in terms of f here. We know what f is here, that function, we've got that up here, but we need the differential of f, don't we, df dt, to sub into there. So let's go ahead and do that. Here we go. So if our general solution for f is that, if we just differentiate it, we're going to get df by dt. Here we are in blue. And we can take these two expressions we've got for f and df by dt and substitute them into the equation r. Yeah, so that bit's going to go in there, the blue, and the yellow is going to go in there in place of f. And if we do that, we get our two lines. This lot here is going to come down into there, r equals, and the yellow is the minus 0.1, there it is, times the f value. Now we can tidy that up. Let's have a look at tidying this up. And we can collect terms, can't we? So we've got some terms here that are in cos. There's a cos term, there's a cos term, there's a cos term. So if we collect those up, we get these three coefficients, which will tidy up, won't they? Because I've got I've got a 0.15a there, and I've got a negative 0.1, negative 0.1 there. And then if I look at my sine terms here, I've got a sine there, a sine here, and a sine there, and if I collect up those three, there we go, I've got those three coefficients, which I can then tidy up and simplify. Here we go, so my 14, that was my 0.15a, subtract 0.1a, there we go, so I've got a full 0.14a there, and I've got a 0.14b there. So now I've got two general solutions for these two equations in f and r, and here are my general solutions for f and r. And you can see, look, these a's and b's are connected between the two equations. Yeah, they're not separate, it's the same a and b. So how am I going to get my specific solutions? Well, I'm going to put in my initial conditions. Let's assume we've got 10 foxes and 1,000 rabbits at the start. Now if we take our f equation, there it is, and we substitute in t equals 0, f equals 0, so I get 10 equals some exponential e to the 0, which is going to be 1. This cos here is going to be 1, that sine here is going to be 0. Therefore I've got 10 lots of 10 equals a, so I know what a is. A bit more difficult for the r equation, t equals 0, r equals 0. Substitute in here, make t equal to 0, so my cos is 1, my sine is 0, and this exponential here is going to be 1, so I get this expression here, 1,000 equals that, multiply it by 1,000, divide by 0.4 rather, and I get this one. And I already know what, so it's a combination of a's and b's, isn't it? Now I already know a is 10, so if I substitute that in, I get b equals 1152, and therefore I have my specific solutions. Having subbed those values back in, I get those two as f and r. Okay, so I've got my original differential simultaneous equations, I've got my f and r, and I can substitute, so I can present those in a graph. Here's the graph. So what the hell's going on here? Well, let's start off with foxes. So we started off with 10 foxes. Because there were loads of rabbits, they ate them, so the fox population grew, and at the same time the rabbit population dropped, and we've got this oscillation going on here, haven't we? There's the exponential growth part. That's the e to the 0, what was it, 115, was it? I can't remember exactly what it was. It might have been 15. And here inside we've got our oscillation going on inside it, haven't we? In here. Now there's a bit of a tricky one here, because if we think about it, looking at these rabbits here, at this point we've gone to 0 rabbits. These are negative rabbits. We can't have negative rabbits, can we? And foxes come down and they get negative populations of foxes as well. So this model crashes at that point, doesn't it? But if we look at the graph of what's happening, if we just graph the foxes on this and the rabbits in that direction, well, we started off here with 1,000 rabbits and 10 foxes, and then each year as it goes along, or each period of time, it switches over. So now we've got fewer and fewer rabbits and more foxes, until it crashes there, because we can't have negative values. So these quadrants make no sense, do they? So we've just got to watch out for real life problems here, haven't we? So there we have it. Here's the summary page for you to look at. We can create some differential equations. We can solve those differential equations, get a second order differential equation. I would add, compared to the example I did, I've got some constants on the end of these differential equations, and they create for us a particular integral to solve as well, don't they? Because we can solve our auxiliary and we can get our complementary function here for f and r, but we can also have some form of constant from that, from our particular integral. And remember, these a's and a dashes and b's, they're all connected, so we've got to leave them like that. So there we have it. Best of luck. Next video we'll cover uses.